Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at the double angle identities for sine and cosine. So I'm going to start off with sine of 2 theta. So this identity is very useful in solving trig equations as well as in calculus. So I'm not going to derive the identity, I'm just going to tell you what the identity is. And if you're interested in how it's derived, it's derived using some other identities. So it's something you can check out on your own. But I really want to look at recognizing when this identity is applicable. The same thing with cos of 2 theta. Very important identities, very useful. So first of all, sine of 2 theta, it can be proven that that's actually equal to 2 times the sine of theta times cos of theta. So if you had certain expressions that you might want to use this identity to simplify, for example, if I had 2 times the sine of, let's say, 3x times the cos of 3x, we could use this identity to express this as, in this case, my theta is 3x. So I know that 2 sine of some angle, cos of that same angle, will equal sine of 2 times that angle. So this will be equal to the sine of 2 times my angle of 3x. So this will be equal to the sine of 6x. So it will be necessary for you to be able to recognize that. Similarly, you might get an expression like this, sine x times cos of x, and you might not realize immediately that we can use this identity because you don't have the 2 there, but we could write this as 1/2 times 2 times the sine of x times the cos of x. So I haven't changed its value because I've multiplied by 1/2 and by 2, so it's still equivalent to this, but now you can hopefully recognize that this is equal to this. So this would be equal to 1/2 sine of 2 times my angle is x, so 1/2 sine of 2x. In a few minutes, we'll take a look at examples of where we can use this identity to prove other identities. Before I do that, I want to take a look at the double angle identity for cosine. And it's defined as cos² theta minus sin² theta. Because of our trig identity, cos² theta plus sin² theta equals 1, I can actually write this identity as 2 other identities. So I could replace cos², if I manipulate my Pythagorean identity, it would be equal to 1 minus sin² theta. So if I had 1 minus sin² theta, written for cos² theta, and then I continue and simplify, this will be equal to 1 minus 2 times the sine squared of theta. So that's a second form of that identity. I could get a third form of the identity by replacing the sin² theta with 1 minus cos² theta. So cos of 2 theta would equal cos² theta minus, and then instead of sin² theta, I'm going to replace it with 1 minus cos² theta. And when I expand, I'm going to get minus 1. A negative times a negative is a positive. I combine like terms. So cos of 2 theta is also equal to 2 times cos² theta minus 1. So I actually have 3 identities for the double angle for cosine. These 3, and those are going to be very useful and important in trig equations and also in calculus. Let's take a look at proving other identities using these double angle identities. I've written the identities at the side here, the double angle identity for the sine function and the 3 double angle identities for the cosine function. I've changed from theta to x simply because I want you to be aware that it could be x, it could be theta, it could be alpha, it could be beta. Don't get hung up on whatever they call that angle. Using those identities and other identities that we've already talked about, let's do some more identities. So for example, if I was asked to prove that this is equal to this, I'm going to work over here and I'm going to factor. Remember that if you have a difference of squares, if I have a squared minus b squared, that's equal to a plus b times a minus b. So I can think of this as being cos² θ squared minus sin² θ squared. So therefore, when I factor this, my factors will be cos² θ plus sin² θ times cos² θ minus sin² θ. I'm just plugging into my factors. So I look at my first factor, cos² θ plus sin² θ. We already know from my Pythagorean identities that is equivalent to 1. I look at my second factor, cos² θ minus sin² θ is equal to cos of 2 theta. And I'll just write that without the factor of 1. So I've proven that identity. In this example, I am going to try simplifying this expression to equal that. And what I'm going to do here is I'm going to break this up into factors. So I'm going to write this as 2 times 2 times the cos of x times the cos of x times the sine of x times the sine of x. Then I'm going to write that as 2 sine x cos x times 2 sine x cos x. So I'm just moving the factors around, which I can do. Now I'm going to take a look at this first factor, and I know that that's going to be equal to the sine of 2x. I can do the same thing with this factor. It's also equal to the sine of 2x. And I can combine those and write it as sine² 2x. And my proof is done. When you're doing these proofs, always keep in mind what you want to end up with. I knew that I wanted to end up with sine² 2x, which is the same as sine of 2x times sine of 2x. So knowing that, that's how I decide often how I'm going to start my proof. Okay, in my next example, I have 2 plus cos of 2 theta over sine² theta, and I want to prove that it's equal to this. So when I'm working with cos of 2 theta, I have a few options, and I actually am going to do this proof using 2 of those options, and you can see that you can still prove it. One way is more efficient than the other way. So if I were to use the first identity, I would have cos² theta minus sine² theta. Now, when I have fractions, if I have a plus b over c, I know that that's equal to a over c plus b over c. It's basically going backwards from adding fractions. Once I have a common denominator, I can add by combining the numerators. So I'm going to do that, use that idea in breaking up the terms in my numerator. And then I can express this. I know that cosine theta over sine theta is cotangent theta, and it's squared, so that will be cotangent squared theta minus 1. 2 minus 1 is 1. And if you look at your Pythagorean identities, 1 plus cotangent squared theta is cosecant squared theta. So I've proven the identity using my first double angle cos identity. However, let's do this question again, and let's use this second one. So I'm going to replace cos of 2 theta with 1 minus 2 times the sine squared of theta. I'm going to again break up those terms in the numerator, so that will be 1 over sine squared theta minus 2 times sine squared theta over sine squared theta. One over sine squared theta will be equivalent to cosecant squared theta. Sine squared theta over sine squared theta will cancel, and I'm just left with minus 2 here. 2 minus 2 is 0. So I'm still able to prove it using a different identity. So you may find that your method is different than the way a teacher is doing it, or another resource, or your buddy. And that's fine as long as you're using your identities correctly. Let's try one last example. In this example and in the previous example, I know that I want to get back to just theta. I don't have a double angle in my result. So therefore I know I want to get rid of these double angle functions by replacing them with these identities. So my numerator was going to be 2 times the sine of theta cos of theta. When I take a look at my options, if I choose the first one, I'm not going to really be able to do anything. If I choose the second one, I'm not going to be able to simplify it. But if I choose this, I'm going to end up with something that I can simplify. So I'm going to pick the third option in this case. So cos 2 theta will be equal to 2 cos squared theta minus 1. The 1 minus 1 cancels, so I'm going to be left with 2 sine theta cos theta in the numerator. In the denominator, I'll just have 2 cos squared theta. I can cancel a 2 out of the numerator and denominator. I can also cancel a cos theta. So I'm left with sine theta over cos theta. And that is equal to tan theta. So if you choose a different identity and you get stuck, then just go back and try one of the other ones. Familiarize yourself with these double angle identities. You're going to find that they're very useful and very important, as well as the basic identity, the 11 basic identities that we've talked about already. I'm going to move on to solving trigonometric equations next video, and we're going to be using all of these identities in the next video. So practice these, and we'll see you then.